Welcome to the rollup revolution. So the main question, the main thing we're going to talk about is what are rollups? You might have heard about them, and you might have heard that they're secure, decentralized, scalable. And the question we're going to ask is, how does that work? Is that even true? Because as young entrepreneurs, you probably talk to a bunch of people from different ecosystems, different blockchains, and they will all say that their blockchain is the best, that it has no problem, that it's secure, decentralized, scalable, the future of money, and that it will make you rich. So, you know, it's important to understand these claims and what's actually true and what is not true. And as for myself, I want to explain technically how rollup works so that you at least can have confidence when people say rollups are the future, or rollup are scalable, rollup are a real solution that works. So that I'm a technical person, so that will be my perspective. So small teaser, what we're going to talk about. What's a blockchain? We're going to go there. Ethereum, my favorite blockchain, currently does not scale. How do we fix that with rollups? How do we fix something called the scalability trilemma? You might know that there are two kinds of rollups: zero knowledge rollups or ZK rollups and optimistic rollups. What's the difference? And finally, this is a bit more technical, but how does fault proofs, which is a system that makes optimistic rollups secure, how does that work? Okay, let's start. What is a blockchain? The basic thing of a blockchain is that it's a bunch of nodes, just a bunch of computers talking to each other and trying to come to consensus, so to a shared agreement over something. For Bitcoin, this is just what are the transactions in the blocks and what's the result of the transaction, which is, how much Bitcoin do you all have? For Ethereum, it's the same. It's what are transactions, but each transaction is a program call to a program stored on the Ethereum blockchain. And the outcome is a change in the state of Ethereum. So consensus is pretty boring. It's something we know how to do since, I don't know, 30 years, maybe even more. It's a solved problem. The new thing with blockchains is that they're decentralized. Decentralized, it's a bit of a buzzword, but what it means really is that nobody can control it. Right? Nobody can turn down the blockchain, not the US government, not China, not the Illuminati or the reptilians. Nobody can do that. And to be able to do that, there are a few properties. One is permissionlessness, which means anybody can join the network as a node, as a validator. That ensures that nobody can control, because if someone can control who is in the network, this person effectively controls the network. If you do that, you have a problem, though, is that, I'm very clever and I want to control the blockchain. I'm going to go to Amazon, spin 1,000 virtual machines, and these are going to be 1,000 validators. And with those, I'm going to take over the network. You don't want it. You don't want people to do that. And this is a problem called Sybil resistance, or if I do what I said and make the machines in Amazon, that's a Sybil attack. And so the solution to that is basically to make it very expensive to run a node so that nobody is rich enough that they can run half the network and take control of the network. And there are two solutions to that currently: proof of work, which is basically make it expensive because you need to buy hardware and electricity so that you can solve the proof of work problem, which is basically finding a hash that fits certain condition, and that's very computationally expensive. That's great. It's a very elegant mechanism, but it's also very bad for the environment because you just burn all that electricity for not much of a result. The alternative is proof of stake, which is if the only thing that is required is that it costs money to be a node, why don't we just ask people to lock money instead? And then we'll give them the ability to validate the network, to come to consensus based on the amount of money that they've locked. So that's Sybil resistance, just make it expensive for people to participate in consensus. You also want people to participate, because even though you have a permissionless and Sybil resistant system, if nobody's interested and you got only 10 participants in the consensus, that's not enough. So people need to participate. And finally, something that's great also is to be able, as a user of the blockchain, to verify the blockchain. So not only trust that the validators are doing their work, but also be able to get the results of what they're doing and check on your own, I mean, on your computer, if that's correct. Does that make sense so far? Is there any question? All right.
Makes sense, yes.
Okay, so that's the basics. So that all that's very great. The problem is that it doesn't really scale. Ethereum, if you use it recently, it's very expensive, $2 for a transfer, $10 for a swap. And that was, you know, a good day. On a bad day, it's like twice as expensive. Some people will say that this is because of something called the gas limit. The gas limit is the amount of computation you can do in a block. And currently the gas limit is very low. Why don't we just increase the gas limit, right? We could easily, you know, multiply it by 10, no problem. All the validators can handle that easily. The problem is that the Ethereum Foundation, and I shouldn't say the Ethereum Foundation, but really like the technical leadership of Ethereum agrees on one point, that they want the user to be able to validate the blockchain at home. So that's something you can do. If you want to try it, you can run a node. You only need a 1 terabyte SSD. That's like the big requirement. Maybe now it's 2 terabytes. So that's the expensive fix, but that's like, you know, 200 euros you need to pay for that. And then you can validate the blockchain on your laptop at home. And they want people to continue being able to do that. And that's why they don't increase the gas limit, because they want to preserve this aspect of decentralization. So we need another solution to scale the blockchain. Okay, so to illustrate the trade-offs that are involved, there's this famous thing called the scalability trilemma. I don't love it, but people love triangles. So, you know, it sounds cool, it looks cool. And basically the idea of the scalability trilemma is that there are 3 properties, and you can only, with a simple system, you can only have 2 of them, right? The 3 properties are decentralization, scalability, and security. Scalability is the easy one, is how much computation can you do? And so this picture comes from an article from Vitalik, which I've linked here. Does this work? Oh, yes, it works. Nice. And so the way he says scalability, like the litmus test of scalability, is that you can do more computation than you can do on a laptop. And why this is important is that you still want to validate on a laptop, but you also want the blockchain to process more than a laptop can process. So there's this conflict there. Decentralization is, you know, can you validate the blockchain yourself? Can you be convinced that it is correct? So, you know, there's this motto in the blockchain that is don't trust, validate, you know, like if someone tells you that it's correct and you have to believe them, that's bad, and you should be able to verify by yourself. Another measure of decentralization, and this is really a measure of decentralization and security at the same time. So this thing is called the Nakamoto coefficient. It's how many people does it take to rug you? How many people does it take to violate the rules of the blockchain? To, you know, insert incorrect transaction that give all the money to someone, for instance. And then security is, you know, Vitalik defines it, what percentage of the node have to defect. So, you know, if you have 10,000 validators, does it need 50% of them? Is it 10% of them needs to defect to work together to steal the money? So those are the 3 properties, and then you can see a few trade-offs. The classical trade-off is to have decentralization and security, but not scalability. So that's Bitcoin and Ethereum. Then you can have multi-chain ecosystem. These are decentralized and scalable. They're scalable because it's a lot of small blockchains that talk to each other. It's scalable because you can always add one more blockchain. It's decentralized because there's a lot of validators across all the different blockchains. It's not secure because if any blockchain is compromised, then the whole thing is sort of compromised. On the other side, so an example for multi-chain ecosystem is the Cosmos ecosystem, if you've heard of that. On the other side, you have high TPS. So TPS is like transaction per second chains, and that would be something like Solana. So these are scalable. They handle a lot of transactions, and they're secure in the sense that it takes a majority of the nodes to defect. But they're fairly centralized because there's not that many validators. And the reason why is that it takes a lot of hardware to validate. You can't validate at home, and so you have to trust the validators, that what the validators are saying is correct. Does that make sense so far?
Yes, sir.
Yeah.
All right, great. So, of course, how do we solve this with rollups? So very briefly, what's a rollup? We can define a rollup as a blockchain that inherits the security of another blockchain. And we will call the inheriting rollup the layer 2 blockchain, or L2, and the parent blockchain L1. So in this talk, I'm just going to assume L1 is always Ethereum. Optimism is an optimistic rollup that uses Ethereum as the layer 1. All right. Okay, so here is a grossly simplified version of a rollup. So we still have the layer 1 blockchain. And if you're rich, so you have a top hat and a monocle, you can afford to use Ethereum. And so you send your transactions directly to an Ethereum node. On L2, though, we have this big node here, the sequencer. And in reality, there can be multiple sequencers, but let's just assume there's one. And the L2 user sends its transaction to the sequencer. The sequencer runs the whole L2 blockchain. It just computes everything. But then what it does is that it sends all the transaction to L1 and also sends the result of the transaction. So the result of the transaction is this thing we call an output root. And an output root is basically a hash of the state of the L2 blockchain. Does everybody know what the hash is and what a Merkle root is? Because this is going to come up again and again. My next slide is about explaining Merkle roots, so I'm prepared.
I don't think all of them know what it is. A hash, yes, but a Merkle root, maybe not. Maybe not.
Okay, so I will explain the next slide. What's important to understand now is that it's a bit less like a signature that you have of the state. And so later you can take a bit of the state and use the Merkle root to prove that this bit of the state did belong to the state. The advantage is that it's much smaller, right? The whole state might be hundreds of gigabytes, but the Merkle root is only 32 bytes. And yet, using these 32 bytes, you can prove any piece of the state that you want. So it's a very powerful cryptographic primitive. So the sequencer posts the transactions and the output root to L1. Next, we have a verifier, in reality, many verifiers. And what these do is that they read all the transaction from L1, the L2 transactions that have been posted in L1. And they rerun everything the sequencer did. So they just check his work. They rerun the transaction and they derive the output roots. When they derive the output roots, there are two results. Either the output root is the same as what the L2 said it was. In that case, everything is fine. Or it's different, which means that the sequencer cheated or has a bug. In that case, the verifier will start something called a fault proof. And this is something that is done on L1 and that we will talk about later in a few slides. The last point I want to make on this slide is that sequencers and validators, they are beefy nodes. They're big nodes. They can do way more than a laptop. And so this is something you cannot run at home. And we will see the implications of that. So Merkle root. So basically, a Merkle root is a way to reduce a trie to a hash. What's a trie? A trie is a way to store key and values, key value pairs. So here we have a very simple trie. And basically all the keys in this trie are 2 bits, right? So if you go here, you have key 0, 0. If you go here, you have key 0, 1, 1, 1, 1, 0, sorry, and 1, 1. So if I query the trie and I want key 0, 1, it will go through here and it will send me this L2 thing. The way you reduce all of this into a single hash is that basically you start at the bottom, so say with L1, you make a hash of that. And that will be stored in the parent node. And then if you have a node like here, its hash is the hash of the 2 hash of its children. And the same for a top hash, it's going to be the hash of its 2 children. And so, recursively, you just hash everything together such that this encodes the whole trie. And for this, we use something called a cryptographic hash. And an important property of a cryptographic hash is you can't invert it easily. So if you have this thing hash L1, you can't find L1 from it. I mean, it's possible, but it would take you theoretically like, 1,000 years using all the computers on Earth to find it, which in practice is impossible. So you can always go from data to its hash, but you can never go from the hash to the data. And going from the hash to the data, it's called a preimage. So L1 is the preimage of hash L1. This will come back later also. Does that make sense, at least broadly?
Yes.
Everybody?
Yeah,
Don't be shy.
actually, I think 90% of them are developers, so I guess they should know what a Merkle root is.
All right.
I guess.
Okay.
You know.
Yeah, because I did the presentation and then later this came up a lot and was like, if they don't really understand this, it's going to be really confusing. So I don't want to make sure. Okay, so the short version about the fault proofs. So one point I will make repeatedly is that the security of optimistic rollup, they rely on there being a single verifier that is honest. So you only need one of them. This is a very different security assumption from the rest, but we'll come back to that. So the way fault proofs work is through something called a challenge game, and it's played between a verifier and a defender. For now, we can assume defender is always going to be the sequencer. And the game is played on a L1 smart contract. I will talk about the fault proof and the challenge game later, but what's important is what the guarantee of this game is that as long as L1, so Ethereum, works correctly, so nobody has taken over the network and is making it do crazy things, then the challenger will always be able to challenge bad output routes. And the result of that is that it will be impossible for a misbehaving sequencer to steal the funds and then withdraw the funds to L1, right? Because everything that is on L2 used to be on L1 and it was bridged over, or it was created natively on L2. Because here we're in the sort of system of L2, we can roll things back, but once the money is on L1, then there's no way to roll back L1, and then we're fucked basically. So this system ensures that bad routes can be challenged, and it's guaranteed as long as L1 is secure, L2 is secure, and the stolen money cannot escape. All right. So is this safe? It is safe as long as, first of all, there is one honest validators, and this is a much stronger security than what normal blockchain have, because normal blockchains, they assume that half the validators are secure or 2/3 are secure. There's also a financial incentive for the verifiers. If they can prove a fault, they can get a deposit that the defender made. And this deposit will be a huge amount of money, will be like at least millions of dollars, because it secures so much money, so it needs to be big. And because of this difference between 1 of n versus n divided by 2, rollups can get away with having much less validators, verifiers. There's also like natural people would naturally have to run verifiers, even if we don't incentivize them in any way. These are infrastructure providers. So you've probably already used Etherscan to look at transactions. Well, Etherscan needs to run a node. We have Etherscan for Optimism. They run an Optimism node so that they can show the transactions. Infra, Alchemy, which are the services that you can send transactions to. The Graph, which is a service that indexes the result of transactions. All the bridges have to run nodes, and it's very important for them. The reason is that if there is misbehavior on the L2 blockchain, the bridges need to stop immediately all the withdrawals. Otherwise, the funds of the people that are providing liquidity for the bridge could be stolen. And so they have really a big incentive to detect misbehavior. Of course, anybody can run a validator. I should keep with the word verifier. Really. Anybody can run a verifier, but it requires potent hardware. Okay, does this make sense?
Yeah, I have a question. What if the L1, so basically Ethereum, is fucked up and 50% of the network is taken? Is Optimism impacted also?
Yes.
Okay.
Yeah, I don't think there's a way to recover from that, really. Yeah. So if that happens, at least two things happen. One is that you can make wrong deposits. So you could just pretend that you sent $10 million and you didn't really, but then you get $10 million credited on Optimism. And the other thing that stops working is the fault proof. So now the sequencer can does whatever it wants. And if he's conspiring with the people controlling Ethereum, he can prevent anybody from making a fault proof.
Okay.
Yeah. All right. No other question?
Yes, I have a question because it's not clear for me the role of the sequencer and the verifier. Let's say that I'm sending a transaction on Optimism. So my transaction will be included in the Merkle tree that you mentioned. And then the sequencer will put this data on the L1. And how's the process for the verifier, and what's the role of the verifier? Because does the verifier verify that the updated Merkle tree that's on L1 impacted with my transaction is good? And how's the process? Because I can send something to the L1 through the sequencer, and it can be corrupted.
So the way it works is that, first of all, the transactions are not put in the Merkle root. So the sequencer sends all transactions to L1 directly. It just stores them. It does not execute them on L1. It just stores them so that they can be read from L1. And it also executes them. So the sequencer executes them. And executing them changes the state of L2. That's the Merkle root. And it also submits that. So it submits two things: the transactions and the Merkle root. The verifier, what it does is that he already has the current L2 state. Is like a normal node. When new transaction coming on L1, he reads them, re-executes them, just like the sequencer did. And then he gets a root, and it will compare that root with the one that the sequencer posted. Does that make sense, or it's not really answered the question?
Yeah, it makes sense. But so maybe you will talk about this later. But the question I have is, so why Rollup are offering me the same security as Ethereum? Because as you said, my transaction is verified by the L2, and then once it is verified, it will be put on the L1.
Yeah, I didn't get the question. So it will be put on L1, but just the data, right? It's not being run on L1, which is the thing that's really expensive.
Okay.
And so, the reason why you inherit the security, in a sense, is that as long as you believe that there's one honest verifier, then you can be sure that this verifier will make a fault proof, and the fault proof will be done on L1, and you can verify L1 at home. So at least you can, if someone challenges the thing, you can be sure that the challenge is correct or not. And you do have to trust that there will be one honest verifier. This is the one thing, the extra assumption of optimistic rollups. If you don't believe that, then it's not as secure.
Okay.
So in this case,
thanks.
Who's the honest verifier?
It can be anybody that
it's
is following what the sequencer posts on L1. But like I said, like at least the bridges, etc., they're doing it for sure.
Okay.
Okay, so how does this solve the scalability trilemma? It's scalable because now we have big beefy sequencers running transactions. It's secure because, well, all of the verifiers have 2 defects. So if there's not a single one, then it's not secure. But if there's a single one, then it is secure. And it is decentralized because, well, this is basically exactly what I just said, right? Like, you can be convinced that L2 is correct because you trust Ethereum. And if you assume that there is one honest validators, then you assume that you would see a challenge that you could verify, basically. Something that people might say after hearing is that rollups are actually very centralized, right? There's the sequencer, or maybe there's 10 sequencers. It seems very centralized. And it does fail on traditional metrics. There are not that many nodes, and running a node is expensive. But what's really important is that to steal funds, to cheat the rules of the blockchains, you would need everybody to be dishonest, everybody that verifies. And also, I will make the point that having one person that is honest is much easier than having half the people honest. Like, if you have 10 validators, 50% security is 5 out of 10. 1 out of 10 is 1. Is this 5 times more secure? I would say it's much more than 5 times more secure, because getting to 100% is always way harder than getting to 90%, which is always way harder to getting on 50%. So that's that's the secret. The one of n guarantee is the secret of security there. All right, so secure bridging. I want to talk a little bit about how rollups really are bridges. And it's difficult to talk about that without talking about what different kind of bridges are doing very briefly. And I want to tell you what are the assumptions that we're making when we send funds from L1 to L2, or we withdraw funds from L2 to L1. We usually say that, deposit and withdraw, although you can create a token on L2 and then you would be depositing it on L1, right? It doesn't have to be in that direction. Before I do this, are there any questions on the scalability parts? Still.
All's good.
All right. So, quick overview on how bridges work. Most bridges, like the overwhelming majority, they, well, I said they're insecure, that's a bit mean, but they rely on a M of n multisig. So for instance, Wormhole, that's a bridge that has 19 verifiers that will look at what you're sending, and they will sign on it. And if 2/3, so 13, sign on it, then the transfer, the bridging will go through. If they cheat, something they can do is like sign. So how bridging works usually, right? Say I want to send Ethereum from Ethereum to, I don't know, Solana. I will lock my Ethereum in a contract on Ethereum. And then I will send a message to Solana saying, hey, I locked the Ethereum on the other side. Give me synthetic Ethereum on Solana, right? How do you know you locked on the other side? Well, in this case, it's because at least 13 people have signed, not any people, like 13 authorized validators have signed to say, yes, it's true. I've watched the Ethereum blockchain and I've seen that he has locked his ETH on the contract on Ethereum. So it's legit. Give him the synthetic ETH. Now, if 13 of these 19 validators, they decide to collude and cheat, they could just sign a fake transaction saying, well, locked 10,000 ETH in a smart contract, give me the same on Solana, but actually it didn't lock the ETH. And so the new ETH you will get on Solana will be completely unbacked. So that's a risk with these systems. Also, a risk is that unlike a blockchain, you can't fork a bridge, right? A blockchain, if someone cheats, takes over, you can always say, well, we're going to make a fork and all the honest people are going to go to the fork. So the version that was taken over is going to lose its value. You can't do that with a bridge. So there are some better bridge designs that are more secure. A better design is what's called an optimistic bridge. And it kind of works like an optimistic rollup with a fault proof. By the way, I didn't say, but why is it called an optimistic rollup? It's called an optimistic rollup because by default, you assume that what the sequencer says is true. And you only change your interpretation if someone does a fault proof. That's why it's optimistic. So you can do that for bridges too, and I'm not going to enter the details, but if you want, you can look at the documentation for Nomad. It explains it pretty well. The trade-off compared to multisig is that it will take more time because you need to allow for a little bit of time for people to do the fault proof, to challenge the bad transfers. And if you're worried, like, it can get really funny. Because not only, so when you have a fault proof, you always have a risk that people are censoring the fault proof. They are preventing your challenge from landing on the blockchain. And so to avoid that, you extend the time needed for the thing to be validated, basically. We'll talk about that because this also happens for rollups. But that's always something you need to take into account when you're thinking, how long should I wait before accepting something that depends on a fault proof? It depends on what censorship is possible. We can do even better than this. We can use something called a light clients. Light clients are things that validate a block from another blockchain, basically. So I could have on Solana, I could have an Ethereum light client. And so instead of sending a message saying, yeah, trust me, I locked the ETH, you are instead going to send an Ethereum block header. And from the block header, you can prove that the deposit was made. But you need to be sure that the block header is legit, right? It's not a fake block header. And this is possible, right? You just need to have a smart contract that verifies that the proof of work is correct or that the proof of stake is correct. So the proof of stake is just that the validator signed the block. And then you need to wait a little bit. The trade-off is the same. You also need to wait a little bit before doing the transfer. And there are technical reasons for that, but I don't think it's really important. This is not very adopted. One reason is that it's pretty expensive to do still. And it's also technically a little bit more difficult. So the only bridge I know that does this is the near Rainbow Bridge. But I think in the future, we'll see more of this because this is like the best we can do without being a rollup, basically. And then the most secure bridge is actually a rollup. And the reason for that is that if the sequencer, so anybody can make a deposit on L1 to L2. So say I'm going to send some USDC from L1 to L2. I lock them in L1 and then I send a transaction from L1 to L2. As part of his operation, the sequencer not only reads transactions from users of L2, but he also reads deposits from L1. These are actually the two inputs. And if the sequencer does not read deposits, that is fraud, and it can be challenged via fault proof. So if I'm a verifier and I see, hey, wait, there was a deposit there, you did not include it, I can make a fault proof and slash you. So this is in the direction from L1 to L2. You also need to consider the direction from L2 to L1. And the way that works is that you basically, when you have an output route from L2 on L1, that output route can be used to prove that the deposit was made on L2 to transfer to L1. It's the same thing as with the light clients, right? It's a little bit like sending the header. But again, we have the problem of censorship. So basically, first of all, we need to wait a little bit to see if someone does a fault proof. Is the route correct? For that, you need to wait a little bit for a fault proof. But then you also need to be sure that nobody's censoring the fault proof. And unlike a bridge, there can be a lot of money on L2, right? Like right now there are a few billions on Arbitrum. Optimism has like $500 million, so that's a lot of money. And so you want to make extra sure that nobody's censoring. And so currently the way that works is that withdrawing money from L2 to L1 takes 7 days. You have to wait 7 days after the output route is received. Could that be shorter? It could probably be shorter, to be honest. 7 days is a bit excessive, but we want it to be maximally secure. Okay, something important to say is that this is not the only way to get money from L2 to L1. You also have all the other bridges, right? All the bridges we talked about before. We call these economic bridges, mostly. And these allow you to go much faster. And the reason why these are economic bridges, by the way, is that they rely on having, well, it depends, actually, that's not true. I will talk about that, but first I want to see if there's any question on the different kind of bridges.
Question, guys?
I have a question, but not about bridges, if it's okay.
Yeah, it's okay. It's fine. It's fine.
So I was wondering how long does it take for a L2 transaction to be considered final?
Okay. The answer is that it depends what you consider final. If you trust the sequencer, it's immediately final. If you don't trust the sequencer, then you need to wait for the transaction to have been sent to L1.
7 days.
At that point, you know this transaction will always be considered. So even if the sequencer lied, if there's a challenge proof, what will happen after is that someone else, maybe another sequencer, will post the real state of the blockchain given the transactions that are on L1. So it will be considered. Now, there's still a potential issue there, which is that, like say the transaction, let's say the sequencer cheats, and then you make a transaction based on the result of the cheating. Say the sequencer suddenly changed the price of ETH. So instead of being worth $1,000, it's worth $1. And you say, well, ETH is really cheap today, I'm gonna buy a bunch. Well, after someone fixes the cheating, your transaction will be considered, but it will fail because it assumes a different price, right? So it will probably revert because of some technicalities in the contract. So it will be final in the sense that it will be considered for execution. The result, though, is not guaranteed. And if you want to be sure that the result itself will never change, for sure, then the finality is like 7 days, right? After 7 days, then you're sure that never, ever will it change. Does that answer the question?
Yeah, great. Thank you.
Right. Interestingly, like Ethereum today, in theory, has no finality, right? Because there's always the possibility that some alien civilization is mining the blockchain, and suddenly they will, make a fork that's more difficulty, right? You can always fork from wherever you want, as long as you have more proof of work. Of course, that's not really realistic, but we call this economic finality, basically. It becomes too expensive to be feasibly doable. Yeah, economic bridges. Do you want to talk about that? It's not really relevant. It's interesting, but not really relevant. So let's skip that for now. Okay. You might be wondering about ZK rollups because there are two families of rollups: optimistic, which I've explained to you until now, and then zero knowledge rollups, which are based on zero knowledge proofs. I realize I should probably have explained what a zero knowledge proof is. Basically, it's a way to prove the result of a computation without necessarily revealing all of the inputs. It's a little bit magical. And something really great about zero knowledge proofs is that it can take less time to verify the proof than it takes to run the computation that is being proven. So you can run a very expensive computation, make a proof for it, And you can verify that in less time than it takes to run the computation. And that's really the key thing that allows ZK rollups to work. I should have put that on the slide, I just forgot. So the ZK rollups, they use this zero knowledge proof to convince you that the output roots are valid. So you don't need any verifier anymore. The security is absolute. I mean, as long as there's no bugs, of course, but if you assume everything's correct, the security is absolute because you don't even need a verifier. You just verify the proof in an L1 smart contract. And this is, it's not actually cheap, but it's cheap enough that's practical. Another great thing is because you don't need a verifier to do a fault proof. You can immediately be sure that the output root is correct, which means you can withdraw instantly and you don't need to wait 7 days. This sounds awesome. ZK rollups are the best things ever, and optimistic rollups are crap. So why are we not all building ZK rollups? That's a great question, right? The problem is that it's not really scalable yet, and it's not really cheap enough yet. So verifying the ZK proofs is cheap, but generating them is extremely expensive. It's like 10,000 times overhead. So if you have something you can verify on your laptop, generating the proof for that, you need 10,000 laptops now. So that's pretty bad. And this limits scalability. And the reason we have rollups in the first place is to scale Ethereum, right? So this is a bit of a problem. And ZK rollups are also fairly expensive. Right now, like today, it's not really a problem. Because when you go, for instance, in Optimism, the price you pay for a transaction, 95% of that, it's price we pay for storage on L1, to store all the transaction on L1. That's what's really expensive. However, we have a solution for that, which is going to make it much cheaper to store data on L1. This is called Deng sharding. I've wrote more of this in a bit, but then I didn't write slides about that. I think this is long enough as it is. But if you want to ask me about Deng sharding, and Deng sharding is a solution that will reduce the costs to store data temporarily on Ethereum by 100 times. When that happens, then the cost of computation becomes significant again. And the 10,000x overhead really becomes hurtful. So one of these two problems you can kind of work around, which is scalability. So you can have layer 3 rollups running on the L2 ZK rollup. And so basically it's just like an L2 for L1, but it's L3 for L2. And what that gives you is that it allows you to parallelize the proving. So you can prove the L2 and the L3 separately in parallel. The problem if you do that is that you lose something called atomic composability. So, on L2 or L1, if you want, you can just borrow from Aave and then swap on Uniswap and then use some other service and do a whole bunch of things in a single transaction. And it's done atomically, all or nothing. If you have an L3, suddenly you can't do things on L3 and L2 atomically. That's no longer possible. So you lose atomic composability and you fragment the liquidity. So if you have Uniswap pools on L2 and L3, well, they will have less money in each of them, right? And so when you make a trade, the price you're gonna get is gonna move more. So if you make a big trade, that's probably not a problem for any of us yet. We're not probably super rich, and so we don't trade like tens of millions of coins through Uniswap. But if you're a whale, this matters a whole lot. So it helps, but it's not perfect. And so, when can we expect ZK rollups to be ready? Today it can already be useful for some use cases, to be fair. If you need fast withdrawals and you're okay with limited throughput, you can use them. So Starkware has a product they call StarkX, which is basically ZK rollup technology that they license to people.
Yeah, we have Henri from them coming in 2 weeks. Can I explain what Starknet, etc. Yeah.
that will be fun because you'll have the the two versions. But to be fair, StarGeeks is a nice thing. It's not really a ZK rollup though, most of the time, because they don't actually post the transactions to L1. So you have to trust them that they will provide you the transaction if you want to verify. Still, that's a trade-off that makes sense sometimes. But so yeah, when ZK rollups become realistic, well, advances in ZK algorithms, and then they get advances in hardware that computes the proof. And I think we're gonna hear a lot more about something called ZK mining in the future. So it's possible there will be a market for people that put the hardware toward generating ZK proofs. I think it will be interesting to see how that evolves. So spicy questions. Do we really need ZK rollups? Because it sounds really good that you can withdraw instantly. It does, but in practice, it's a bit dangerous too. The fact that you have a delay, it does act as a guard against hacks and bugs. And for instance, Optimism had a bug a couple months ago. And it was reported to us by a white hat hacker, so we could fix it, and there was no problem. And we did pay that hacker a really good bounty of $2 million. So it was like the most critical bug. But basically,
yeah, white hacker. So drop everything to be a hacker.
But if this bug had been exploited, well, nothing would have happened on Optimism. But if we had instant withdrawal, someone could have instantly withdrawn all the Ethereum from L2, which is pretty damn bad. But since we have a 7-day challenge period, we could have like fixed the system in that time. So withdrawal like actually can be very useful as a security. All the non-rollup bridge, they still get fucked by such an attack, right? But the thing is that the liquidity in the non-rollup bridge is fairly limited. It's typically not it's not 100%, and it might not even be 10% of the total amount. So it just limits the damage really much to have that security. And then a counterpoint of why that might not be true is that bridging via these other bridges, it might not be good enough. So if you want to bridge, tokens are very famous. So if you want to bridge Ethereum, USDC, SNX, Uniswap tokens, Uni, all that is possible. But if you have this weird token from your project that 200 people are using, probably there's no way to bridge it. And so you have to wait 7 days if you want to at least go from L2 to L1. I think there are solutions around that. And if you're curious, you can ask me about a solution for bridging NFTs and low liquidity tokens. But it's an open question. I think people can argue about that for a long time. And I don't want to say there's a definitive answer. So in reality, I don't know if we really need ZK rollups, if they're coming, if it's going to go. But I think I can tell you what we're thinking on Optimism, which is that we don't think ZK rollups is ready. When it's ready, we might just switch to a ZK rollup, honestly. Like I think it's a pretty cool technology. And it can be used for a ton of things. So there's ZK rollups, but then there's applications of it that make a lot of sense. And we're gonna use that for sure. Like I already know one thing that we're gonna use ZK zero knowledge proofs for in our optimistic rollup stack. So in the future, probably when you run the fault proof on Optimism, as part of that, we're going to do a very small zero knowledge proof to prove something very specific. So yeah, if you want to learn about something that's really cool, I recommend looking into zero knowledge proofs. All right, let's do a break. Any questions so far? All right.
No question, guys. I have a question. Like, if we speak about the optimism landscape, is there any concrete application, like people that are building on optimism and product that can be used by random users, or not yet, or just a bridge and that's it?
No, there's ton of apps, and there's all the apps that you would expect from L1. You know, like we have Aave for loans, you have Synthetex to make synthetic assets. There's a lot of things that are still, you know, the most popular on Optimism are sort of like smart finance, I like to call them. So things like option protocols, perpetuals, so it's sort of DeFi. We also have a great NFT marketplace. It's called Quixotic. That's really hard to spell. It's like Quixotic. Quixotic. It means overly optimistic. And they're like sponsoring a lot of new cool NFT initiatives. So there's a cool NFT community. I mean, we're hoping we get more use case, and especially things that don't really work, that are not DeFi and just NFTs, because everybody knows about that. And things that will leverage the fact that the fees are cheap. So right now it's still fairly expensive, I would say. Like a swap or something will cost you 50 cents. And that's still too much. But once you get the new data availability solutions, that's the thing that's going to cut the cost to store on L1 by 100x. Then it will get really, really cheap. And then I'm excited to see what people come up with there. The best way to learn about that is just to go to the official website. There's like a ecosystem page, and there's a list of apps that we populate if you want to try some things out.
I have a question for you on Norswap. So you said that if sequencer behave not in a good way, they're slashed. But are they penalties like we have on validators on ETH proof of stake because they are too slow or that kind of thing, or it's really only slashing for the time being?
It's only for fault proofs. If they are too slow, there is two things that can happen that can help. One is that in practice, we're going to decentralize the sequencer. So there will be multiple sequencers. So one or even a few of them going down is not going to affect the liveness, because all the other sequencers can take over. The other thing that's going to happen is that, say even all sequencers go down at the same time, you could be afraid that all your money is stuck on L2 and now there's no way to get it back because there's no sequencers. What happens there is that you can do deposits on L1, and these deposits, I mean, we call them deposits, but really they're a general mechanism to make an L2 transaction from L1. That's what they are. And so you can initiate a withdrawal from L2 from L1. So on L1, you send the transaction that will say, well, withdraw my money, and that will get executed. You still need a sequencer for that. Like, you need someone to submit an output route at some point.
But in that case, if I can just set up a sequencer myself and launch the transaction, right? Exactly.
That is the idea, is that there will at least be a fallback mechanism that says if no output routes are being posted, then anybody can post an output route.
Okay. And how the sequencer, like, first time being, I understand that it's more or less centralized because you are still young, but then when you will have, I don't know, maybe hundreds of sequencer, are you going to select only one for each block, or are they going to go in parallel and pushing on the same contract?
That's still being discussed.
Okay.
I think right now the plan is to just do something called a leader election. So there will be one sequencer responsible for a single block. That's one possibility. One something that's very simple is to use the Tendermint consensus algorithm.
Yeah.
That's what Cosmos uses.
Mm.
And this works really well when you don't have too many nodes, which will be the case of the sequencers, right? There's never going to be hundreds of thousands of sequencers, so we can use that.
Okay.
Yeah.
Okay, thank you. And one last question for the sequencer: are they going to be like? What are the technical, like the hardware technicalities? Like, is it going to be runnable on cloud providers, or is it going to have a like your own hardware on premise and you cannot run it on cloud providers?
So everything's open source, so you can do whatever you want. As for how much hardware is going to take, it depends how successful we get, right? Right now, I think you can still run it on a laptop.
Okay.
Pretty sure, but.
Okay, thank you.
All right. Anyone else? Okay, let's talk about fault proofs. So so far we said that fault proof is the challenge mechanism, and we didn't really say how it worked. We left it a little bit vague. Now I kind of want to explain. This is maybe the most technical part, but I'll try to keep it simple. So the way it works, the verifier runs the L2 node software, just like we said before. It's a replica of the sequencer. It checks over the sequencer work. And so if it finds an output route that's different, it initiates the fault proof. Right. To do this, you will use a tool that we call minigeth. It's called minigeth because geth is the shortcut name for Go Ethereum, which is the most used node software for Ethereum. And we have our own version of geth for Optimism, and so minigeth is a modified version of that. So it has three inputs: L2 block number, the transaction batches, and the deposits. Transaction batches are the transactions sent from L2 to L1. So what you do with these inputs is that you do the derivation of a single block, basically. So like I said before, you just re-execute transaction, derive the output route. A side effect of doing that is that you can derive what's called an execution trace. And the execution trace is a list of all the steps that you did to derive the output route. And so a step is like really an assembly instruction that you executed. The other thing that minigeth can be used for is to, at any step in this execution trace, you can generate a Merkle root of the memory, the whole state of minigeth. So everything that's in the memory, everything you need to continue the execution from that point onwards. So this is a tool that we're going to use. And the way this works is that the verifier and the defender, they play a challenge game on that one. It's sort of a ping pong game where they send something and the other one sends something back. So the defender is usually the sequencer. It could be anybody that has a big enough deposit that will be slashed if they lose. But let's just assume that the defender is the sequencer. It will be easier. So the challenger, so that's the verifier that wants to make a challenge, he initiates the challenge by posting his output route. His output route is going to be different from the one from the sequencer because otherwise it wouldn't be a challenge. And he's going to post the Merkle route for the final state of minigeth, basically. After the last step, what's the memory? Do a Merkle route to that. You're also going to post the Merkle route of the memory at the middle of the execution. So if you think the execution is 10,000 steps, step 5,000, you send 5,000, then you send the Merkle route of the memory. And so then the game starts. So these, this array over here, that's the execution trace of the challenger. And this array at the bottom is the execution trace of the defender. And so each square is an execution step. And so the first step is, as I said, the challenger sends the Merkle route of the memory. The next step is that the defender will respond. with the same thing. And then you compare them. And there's two things that can happen. Either they're the same or they're different. In this scenario, I've assumed that they're the same. And so you take what's left in the execution trace, so this part on the right, you split it in two, and you go again. So the challenger sends the Merkle root at 75%. Defender does the same. Now we're going to assume that it's different. And so the process repeats. No, this area here is left. You split it in two, send the Merkle root, send the Merkle root, compare. And you keep doing that as many times as is needed until you find a single step that you disagree on. And for the single step, you agree on the memory before the step, and you disagree on the memory after the step. And so you know that you're in conflict about the outcomes of this step. What you can do once you have this step is that you can run that step on L1 and basically see who's right. By the way, interesting anecdote, this is not in the slides. We used to have a system where we would rerun the whole transaction on L1. So we can do a whole block on L1. That's just too much data, but we could do a single transaction. And this was very complicated for a number of reasons. It was still very expensive. And yeah, like the overheads are big, so you have to do it in a certain way, and that way makes everything difficult. I can answer your question about that if you want to know about it, but just so you know, that's something that was tried, and there's a very good reason why we don't do it that way, even though it seems simpler to just rerun the whole thing. And that's why we play this game. So the next step is then to execute the single instruction. And for us, like or steps or instructions, there are MIPS instruction. MIPS is a instruction set, and we just picked MIPS because it was very simple. So you can write an interpreter for it on chain that is simple. And also Go Ethereum, as the name implies, is written in Go, and it's very easy to compile Go to MIPS. So that these two things together make it really easy to use MIPS. But okay, when you execute these instructions, it needs to access the memory of minigeth. The memory of minigeth is obviously not stored on the L1 blockchain. And so basically what you have to do is you have to pre-supply all the bits of memory that are going to be accessed by the instruction. It's just one instruction, right? So one instruction, for those that don't know, it does really basic thing like load this value from memory into a register, store this value from a register to memory. It's like, it will touch 3 or 4 area of memory at most, because it also needs to read the instructions, need to update some counter. But so it's really like 3 or 4 things from memory. And so you can pre-supply them before you run the instruction. And you can be sure that what you supply is correct, because you could just supply, garbage. How do you know? Well, you know because you agreed on the Merkle root of the memory before the instruction, and you can use the Merkle root to prove that the bits of memory that you're sending are correct. And because the challenger and the defender, they agree on that, there can be no possible disagreement there. Another thing that you need to access sometimes is the inputs, right? Because the memory does not magically contain the L1 transaction, the L2 transaction that were sent on L1, right? You need to get that from L1 directly. And the idea is the same. You will pre-submit them, just like the memory. But the proving that they are correct is a little bit more difficult. And so basically we use something called a preimage oracle. And a preimage oracle is you send some data and you say this is a preimage. The L1 contract computes the hash of this, and it stores a binding from the hash to the preimage. And then minigeth can call the preimage oracle to get from a hash to get the preimage. Remember that normally you can never get a preimage from a hash, but here it was submitted in advance and stored, and so we can get it. Okay, this is the last slide. So if you're like sweating profusely right now, don't be worried. Your suffering is almost over. I just want to illustrate this idea of the pre-measure oracle because it's very difficult. But basically, you execute the instruction on an L1 contract. The L1 contract has access to this opcode, this Ethereum virtual machine opcode called block hash. And this gives you the hash of the last L1 block. If you use the pre-measure oracle, you can get the block header via this block hash. This block hash also includes the hash of the previous block, which you can use via the pre-measure oracle to get the previous block header. And you can go back like this as many times as you want. Each block header also includes a transaction Merkle root, which is the Merkle root of a trie that stores all the transactions. Basically, the key is like the index of transactions. So, key 0 will map to transaction 0, so this will be the first transaction, this will be the second transaction, etc. So say that I want to read a transaction from L2 that the sequencer submitted to L1 on block 41, okay? So we submitted this transaction here, and this contains the transaction batches that I'm interested in. So on block 42, we're just assuming it's the next block to make it really simple. On block 42, someone says, wait, this is not correct. I'm gonna do a fault proof. And normally this is not possible, right? Like, because it's a ping pong, basically you need to wait a bunch of blocks until the challenge game is complete. But let's assume it's the next block, you're executing the single step immediately. And during the single step, well, you need to access this batch somehow because the instruction you disagree on touches the batch. So what you do is that you use the block hash, and then via the pre-measure oracle, so you follow the green arrows, you get this header here. So that's what mini-guess is doing. And then it needs to reach for block 41. So it uses the prev, it uses the pre-measure oracle to get the block header. And then it uses the pre-measure oracle to get the Merkle root. And then it used the pre-measure oracle to get the first node, etc., etc. Each time, the hash is stored in the nodes, and you can get the content of the node from the hash via the pre-measure oracle. And so follow all the green arrows, and at the end, you can access the transaction batch using only this pre-measure oracle. And I'm gonna conclude there. So if you have any questions on this, now's your chance.
Thanks, man. Intense. Who has questions?
I have a question. Mini-get, is it on L1? Like,
so no, not exactly. It's something you run off chain.
Okay.
And you use the results from it to play this challenge game on L1. So
okay.
you use the Merkle roots of the memory to just find the one point in the execution of mini-guess, which happens on off-chain that you disagree on. And then you just do one step of that on-chain.
Okay, so the binary search is on-chain, like in the challenge. And isn't it a situation where it's more expensive, like to run the challenge that what was stolen? Like, because as it's going to be a loop, or you can have in the worst case a lot of transaction. It might be more expensive than if you only store like, I don't know, $500.
No. Well, yes, if you only okay.
You see what I mean?
Yeah, you can always reduce it if you still less than the price of one transaction on.
Yeah, for sure. But let's say I don't know how many transactions on average you do, but at least, I don't know, 5 or 6 transactions or even more.
Yeah, but like the question here is why would you steal $20 or $100 when you have a bond that's worth $1 million that you will lose if someone challenges you, right? This would make no sense.
Yeah, okay, see what you mean. It's a game theory then.
Yeah, exactly. The whole thing relies on on game theory. Well, I mean, it does not. Like, you can be completely insane and do that anyway, but then somebody's gonna challenge you. So it does not rely on you being rational. You can try if you want, but someone will challenge you. So
okay.
yeah.
And
You go.
Another thing that is not really clear about Minigate, if it's run off-chain, how can you know that I'm running the right version of Minigate and not a version that I rewrote myself that is doing something that I would like? Like, how could you? Oh, because the person that is going to challenge you will have the right Merkle root, and so you must have the same.
Yeah. So what's gonna happen if you do that is that you're gonna disagree on every single memory step. Every time you challenge, you're gonna disagree, and so you're gonna end up at the start. And the very first one, the state before the first step, is hard coded on L1.
Okay.
So that's basically what says what the right version is, right? You should take your version locally, just hashed before the first step, and compare with the one that's stored in L1. If that's the same, you're running the right version, basically.
Okay. Thank you.
I have one question. Thank you. First, how do the sequencers aggregate the transactions? Are they dumb, like they aggregate by time arrival, or is there some sort of mempool, just like on L1?
That's a good question. Currently, they're very dumb. They just do first in, first out, and there's no mempool, so it's entirely private. This is something we have designs for. It's a really difficult question, because once you have a mempool, you start having minor extracted value. I mean, you always have minor extracted value, even if you don't have a public mempool. But once you start having a public mempool, it becomes a bigger problem. And we have projects currently that rely on the fact that the mempool is private, so we can't just make it public all of a sudden. So right now it's first in, first out. In the future, we're gonna order it. We're gonna probably run something like flash bots to extract MEV. We're like making designs for that, but there's gonna be something like that for sure.
Okay, thank you.
So you're gonna do MEV on your own pool?
Yeah. So we're gonna. So this is debated, and there are different plans for different time horizons. I think what's going to happen in the short term is that we're going to run something like flashbots, which lets searchers, they're called, search for MEVs, and then they bid for these opportunities. We are going to do that in a way, at least that is the plan, that does not degrade the user experience. So I think still by default, everybody will submit to a private mempool, so that they can't be sandwiched, for instance, like where someone fronts on them and then backthreads them and just makes their slippage worse. So we're gonna prevent that. And basically, since everything's gonna be through the private mempool by default, really the auction will be for the top of the block. And I think we're also gonna maybe push a public mempool where we're gonna put, on a voluntary basis, transactions that generate MEV. So for instance, if you have a loan protocol, how a loan works. Like you put 2K worth of Ethereum, you get 1K worth of stable coins as a loan, but then Ethereum decreases in value to 1K or something, and then you have to liquidate the loan. And the person that liquidates the loan gets a bonus. And so searchers, they compete to get that bonus. And so probably the loan protocol will want to make that, well, these liquidations come from Oracle price updates. And so the Oracle price updates will probably be public. And then the searchers, they can bid to be included right after the Oracle price update to be the first to get the, to exploit the opportunity, basically. So that's the short-term plan. At least that's what I'm advocating for. There's all kinds of consideration of how easy is it to do, what people needing. So this is not like, the definitive word, but this is how I personally see it. Longer term, we might do something called MEVA, so MEV auctions, where we just auction off the right for someone to create the block. And so, exploit all the opportunities, but you have to pay the protocol for a price to do that. We'll see. I mean, the important thing is to make sure that the person that buys the right does not degrade the experience by doing sandwiching and things like that. But I think we can also handle this at the governance level, where basically we say, well, the rules for people who participate in the auction is that you can't do sandwiching, you can do this and that. And if they're caught doing that, then they can just be banned from participating in these auctions.
Okay.
But how do you draw the line between what will degrade experience for users and what will not?
That is the really difficult question, especially in the case of MEV auctions. This is contentious. I've been debating this with my colleagues, but for the simple flashbots things, my opinion is that it's okay to let searchers bid for top of block and for background. So if they see a transaction, they can bid to be included first after that transaction, but no front running, because you don't want people to snipe you. And also front running lets you do sandwiches. So if you just do backgrounds and top of block, I think that reduces most of the negative things that you see. But not everybody agrees with me. At least some people are like, it's more difficult than that, but then they can never find examples. So far I have this opinion, but it's controversial.
Okay, thank you.
Great. I think Thomas has a question, and then maybe we run out of time. So if you want, you can share your Twitter handle, and maybe even if your Telegram, if you want, you share whatever you want, and people can ask you question in private. But yeah, Thomas, if you have a last question.
Yeah, last general question. I want your viewpoint, Norswap, for the future of layer 2. We often say that layer 2 are breaking composability because if we are working on Arbitrum, we cannot composite with Optimism. Do you see a future, like technically, is it possible for you in your mind that in the future we'll be able to do, I don't know, an L3 on top of Optimism and Arbitrum, when we can have composability between the two L2s or something in that sense? How do you view this future in terms of composability between layer 2?
Yeah, I don't think there's going to be any easy solution for that. So you probably can build some services, but they're not going to be fully like composable at the level of execution. Instead, if you have a specific use case in mind, like, say swaps or some kind of DeFi application, then you will be able to build something that composes. And basically, you also pay a fee to use that service, and the person that builds it will take the risk of it not being atomic, but will be compensated for that risk. That's something that might happen. It is really difficult. I think honestly, and this is a little bit spicy, and also not something everybody agrees on, but at Optimism we think we really want to scale vertically, so make this a huge rollup that has this huge and has basically everything on it, because the solutions for this kind of cross rollup or even cross-chain scalability are really difficult. I should also say that for rollups, there's no really, it's not really different than from cross-chain for any other. They are related by L1, but going through L1 is always crazy expensive. If we have ZK rollups, maybe we can make going by L1 worth it, but it will always be in aggregate, right? Because if you just do it for your own transaction, it's going to be really expensive to go through. And it's not going to be atomic anyway, just fast. So yeah, I think it's going to be really difficult.
Okay, thank you.
Great. So where people can DM you? I guess I shared your Twitter. if it's okay, just
It is okay. It's okay. It's very okay.
Great.
I am Norswap pretty much everywhere, so it's really easy to stalk me. So yeah, feel free to reach out to me on Twitter, even on Telegram if you want. I'm also Norswap, so I'm happy to answer your questions if you want to build an Optimism. Yeah, I have a small developer chat for Optimism. It's not very active, so I'm trying to make it more active. But you know, if you have like ideas or you want people to collaborate with, you can always drop a message in that chat. You know, just message me. I will send you the invite link.
Great. So thanks, Norswap. Everybody say thanks. It was great. This is recorded. I'll send you the link when it's online. Thanks, guy.
Thanks. My
Thanks.
pleasure.
Bye, everybody.
Bye.
See you.